Welcome back to week 2. This is video 3, and we're talking about another example out of the textbook. An automobile wheel and tire are suspended by a steel rod of 0.5 centimeters in diameter and 2 meters long. That's pretty small, actually. That's like 5 millimeters, isn't it? Did I do that wrong? Yeah, that's only 5 millimeters. Anyway, that's pretty small compared to being 2 meters long. It might be freaking wire practically. As shown in this figure, when the wheel is given an angular displacement released, it makes 10 oscillations for 30.2 seconds. So determine the polar moment of inertia of the wheel and tire, right? And so in that case, they mean by polar moment of inertia, they mean the mass moment of inertia. We can expect to try to get units like kilogram meter squared as part of this. So just from observation, without doing an FBD, we could say that we know this is going to have an equation of motion that looks like K over J. Right? This is a simple setup. This is only going to be true for small angles of displacement, but we can go ahead and say that that's what we expect it to be. We can also say that K is going to be equal to pi d fourth G over 32L. We established that in the previous video for a round shaft. And we can look up what the values of those are going to be. The G we could get from a is because it says it's steel, where it is steel rod. These are going to be 80 gigapascals. Is the modulus of rigidity, by the way, if you can't remember that. It's a great name. It's the second cousin to the Young's modulus, but it's the shear version, if you will. Remember, there's a relationship between Poisson's ratio, Young's modulus, and their modulus of rigidity. I think it's a great name. I think I'd like to name a band that, except I'm not gonna. Anything else I want right here? Except maybe I want to make the diameter. It's going to be 0.005 meters, which I believe is going to be 50 centimeters. Is that right? No, 0.5 centimeters. That's what they said. 0.5, which is very small. Okay, so we start off. They give us what the number of oscillations. So the period of one oscillation is going to be 30.2 over 10, because there's 10 of these oscillations and they've timed it. But I like it because that's like, all right, so that's, if you were going to work on this thing, this is really what you would literally do if it was a scenario where you were actually physically able to measure. So the natural frequency that we're measuring is going to be 1 over the period, or 1 over 3.02. I'm going to give him little huggy parentheses, and so that is a 0.3311 hertz. Very low. Wouldn't be able to hear a note. You probably wouldn't be able to hear a note anymore because it's twisting anyway. But anyway, so the circular natural frequency of this thing is going to be 2 pi fn, and I'm not going to write that out. I'm just going to write out what the answer is: 2.085 radians per second. And I've obeyed the rule of staying at least 4 sig figs all the way along. Please bear that in mind. So knowing that the natural frequency is going to be the square root of K over, and this J right here is the polar moment of inertia. I should have made that clearer here. This is the polar moment, mass moment of inertia. Damn, I'm sorry, I should make that clear. It's the polar mass moment of inertia. Say it 25 times fast. If we solve for that, it's going to be K over omega n squared, right? Solving for J. I'm going to solve the K separately. I could just plug stuff in, but I want to see what the numbers are. Pi, I'm going to rewrite it. G. There's also another opportunity to play the units game. They're not a lot of fun. Oh, I didn't do it here? Okay, anyway, we'll do it anyway. 0.005 meters, and we're going to fourth it, and then we're going to have 80 E9, and these are newtons per meter squared. That's what a Pascal is. So there's a gigapascal. So E9 takes care of the giga. The pascals is a newton per meter squared, divided by 32, has no units, and then the length, which is going to be 2. And that's going to be meters, right? So let me quick look at do a little bit of a thing here. So those are going to get rid of 2 of those. Is that true? I'm double checking myself. Where did you go? Oh yeah, no, we're good. And then this is so there's going to be 2 left right here, but that's going to get rid of that. So there's 1 meter left at top. So we got a Newton meter. And for this type of operation, we're going to have a Newton meter per radian. So we wouldn't expect to see any radians as part of that. So we work through the numbers and we get 2.455 Newton meters per radian. Great. Now let's find out the J. You're going to be equal to, I don't have to write it again. We'll go 2.455. Looking very Christmassy. Newton meters per radian, and divided by 2.085 radians per second squared. So we don't really care about the second squared, the radians, right? Well, I said second squared. This is my brain. I was jumping ahead. I mixed it up. It's supposed to be squared, right? Because that's squared up there. And what we end up with is a 0.5646. And just ignoring the radians, because they're not really units, they're kind of like spaceholder for units, we would find that we would get Newton meters second squared. And we're like, well, what the hell is that? Well, we kind of know what we want. We want kilogram meters squared. Anytime you're doing a units conversion type of thing, I think it's a good idea to think of it in terms of F equals ma, by which I mean a Newton is equal to a kilogram meter per second squared. So if you shove the Newton back into this, boom, what you end up finding is you get a kilogram meter per second squared times meter second squared, right? You follow that? Follow that logic? That's the meter part. That's the Newton part. But the second squared cancels out, and you're left with kilogram meter squared, which is what we expected it to be. So let's get a better color. I don't know. Let's use one of those blues. I like this little baby blue thing. J is equal to 0.565 kilogram meter squared is what we have in this sort of like experimentally determined this mass moment of inertia. So we'll call that done.